Yes. Okay. There are things that you can do to make you digest stuff. So I know a lot of people say, I can't play an instrument. I thought I mentioned this. But you just have to realize that it's going to be frustrating, you're confused, but if you keep at it, it sticks. And one thing you can do with all your classes is, if you look at the material before the class, and as you transfer to university, they go faster. And so you kind of, to survive, you look at the material first. You don't totally get it, it doesn't matter, just go through it, keep on going, don't get stuck on it. Just go, I'm gonna prime my brain so that I can see it again. So the second and third time, it does start to sink in. And that's just natural, and that's just the way all of us are, and all your professors and everybody has done that. So a lot of it is sticking with it and continuing on, even if maybe you don't meet your perfection, because life happens, like, I don't know, coronavirus. So I encourage you to try to look at the notes that you took in the previous class, before class, skim over any of that stuff that you do. Anytime you go around, it just starts sinking in. So I encourage you to do that. All right. Again, we probably will go online next week. We've done chapter 1. We now have our refillable pens, environmentally friendly, etc. Yay. But I'll probably get rid of the other ones first. So we've done chapter 3, science. And we're just about to finish up science and the evolution of science. And we talked about Newton's laws. So we had Newton around 1700. And we've got these ideas of acceleration. How can you accelerate? 3 ways, right? So net acceleration is any change in motion. You can increase speed, decrease speed, or turn. That's called acceleration. Force is a push or pull that has to be from someone. If you're walking down the street and you go like this, and there's no one there, then that's really weird, right? So there's someone to blame. The strange thing is, if I let go of this, does it get pulled? Am I pulling on it? It's a little more obvious here. Am I pulling on this? Yeah, because if I don't pull on it up, what's it going to do? Go down. Now I'm pushing on it, right? That makes sense. But why do I have to push on it? Is something pulling on it down? So when I let go, I'm pulling on it up. When I let go, is anything pulling on it? The force is gravity. Who are we going to blame? What's the object? Earth. Every piece of Earth. That's a really strange idea. And if you ask Newton, how does that work? His answer was, shut up. Stop bothering me. No, his answer was, I don't make hypotheses, which was brilliant. It's like, I'm not going to be stuck. Like reading through this stuff. Okay, I'm confused about that. I'll come back to it. I'm going to keep trying. But he wasn't stuck on that. He still will move forward. He could not tell you how gravity worked. But he could write an equation that would give you Kepler's laws. And so we'll see that here a little bit today. Like somehow all of Earth is pulling on it. That's a way of thinking about it. Now 200 years later, around 1900, you got Einstein, who said gravity works because mass warps space-time and things move in that warped space-time, and we're not going to go there. But that took it even further. So far, Einstein's warped space-time general relativity has never failed and has predicted things we wouldn't have expected. Doesn't mean it's absolutely right. We keep testing it. It keeps succeeding. Okay, so we're going to talk about just looking at how things move. And so, looking at how things move, and if you attach this to your lip and pull harder, as this gets longer and longer, it's pulling stronger and stronger. All right. So how do things move? And Galileo did this too. So let's see if we can make some sense of this. we've got Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. We didn't do Newton's first law, right? Yeah. So these are the laws of motion for all matter or objects, not, and this is interesting, not light. Light doesn't have mass. So that's what we're talking about. The laws of matter for all objects. These laws are wrong, but they're really close to right, and they're what we use because they're like basically right. And it wasn't until Einstein that corrected them a little. When you go near the speed of light, you need to correct them with Einstein's special relativity. When you go near strong gravity, like close to sun, you need his warp space-time, and it corrects it. And when you get inside of an atom, you need something called quantum mechanics to adjust that. Who cares? It was a huge advance. No longer are we pulled around by retrograde of Mercury and the god of this and Zeus and whomever. But there's actually rules by which the world works. By the way, I do want to say that when you do physics and everything, physics does not say anything about God. Either way. It doesn't say anything either way. So you can't, it doesn't say there isn't a God, it doesn't say there is a God, but you know, we can kind of look at our own reason for thinking about things. And you test things. So however it is, it is. All right, so there are these rules. So Newton's first law is sort of as follows. If there are no forces, now this is counterintuitive. So some of these make total sense sometimes, and then they trick you. They tricked Aristotle. And so Newton's first law, Newton's 1, let's see, if there are no forces, well, good luck with that. There's always gravity. So imagine, or in space, somewhere deep space, or more likely, if all forces on an object from other objects, you got to be able to blame someone, are balanced, call that equilibrium, and we'll see that again with stars, equilibrium. Then the object cannot, it can't, no matter what, no matter how much you want to, it cannot accelerate. It will not accelerate. If it accelerates, you got to blame someone, something. And that looks like this. The things on the table. If starts at rest or not moving, stays at rest. However, if for whatever reason it's moving, got moving, whatever, who knows, we'll talk about things like that. But if starts moving, or somehow it started, I don't know, then all forces in balance, in either one of these cases, you must have no acceleration, and that would look like this. has to do with speed and the direction it's moving. Same speed, same direction. Aristotle said, that's not the way things, I mean, he was dead, but he thought this. He basically thought people go home and kick back. Things, objects want to go to their natural place. Fire goes up, air goes up, water goes down, and earth goes down below the water. They sort out, so this is just going home and kicking back. He said, watch. See? You can push it, you can make it move, but then it just wants to sit where home is, where its natural place is. And Galileo really deserves credit for this because he was doing these experiments. And so what happens is you do this and you smooth out the surface. And so surfaces have these little grooves that make you slow down. If you make it smoother, you'll slide farther. If you make it smoother, you'll slide farther. If I go like this, not very far. If I go like this, farther. Now I take a hockey puck and I put it on ice and it's just going to keep on going. Very little slowing down. And it doesn't turn. See, we were told that things go around Earth because they go around out in space in perfect circles. Why? Because that's what they do. Well, if you test it, you find no. Things don't go in circles on their own. They go straight. You cannot turn. You cannot increase speed, and you don't slow down. You don't need to keep on pushing something to keep the same speed unless there's another force working against it. So right here, I'm pushing this way, and those little grooves are pushing the other way, and that keeps the same speed, same direction. I have to push in order to balance the other way. Is everybody kind of okay with that? Let me show you another. This is, again, it's fine until it's not. And people speak incorrectly a lot. I'm going to push it, so I'm going to increase its speed, I'm going to accelerate. You can blame me, it's okay. And then I'm going to let go. Is it accelerating when I let go? What's it doing? Decreasing speed and turning. Turning is a way to accelerate, right? So if it's turning, something has to, in fact, let's just put it up to say it, and then we'll look at this. When an object accelerates, we have Newton's second law. And that says it is unbalanced force, or unbalanced forces, that causes acceleration, that causes you to increase speed, decrease speed, or turn. So a stronger unbalanced abbreviated force gives you more or abrupt acceleration. But what resists the acceleration?
Mass.
More mass I'm talking about the object we're pushing, so more of the object's mass is going to resist more, and we're going to get less acceleration. More gentle change. More of a gentle change. I like to think of an elephant on a big skateboard and a little kid on a skateboard. Which one's harder to speed up? Elephant. Which one's harder to slow down? So this is the interesting thing. The elephant doesn't slow down on its own. But you go, but look, they do. Things slow down. Yeah, but it's not on their own. They're made to slow down because of the little grooves, the roughness of the surface. You make it super smooth, super good skateboard, you're going to go for a long ways. You don't slow down on your own. You got to be made to slow down. You got to be made to speed up. You got to be made to change direction. It's harder to speed up an elephant. It's harder to slow down an elephant. Just try it. And it's harder to turn an elephant. That's what mass is all about. If you push stronger, you'll get a more abrupt change. No matter what it is. But the more mass it has, the less. We're going to pull this all together with astronomy here in a second. You see how it ties to this.
Like your little globe.
Yeah, like my little globe. And rotation is an interesting thing because it's built on this, but in this case, it sits there. Gravity's going down. There's a magnetic force balancing it up. It isn't as though there's no forces, but in space, I should be able to let go and it would sit there. And in space, I speed it up. Once I let it go, it should do this. And even here, what's true, and this is totally misleading and tricky, is that it's just you can't get away from it. These are laws you can't break. You can't break these laws. Yes, Casey.
Your phone stopped recording.
Oh. Did it just stop?
I think it says low power, but I can't.
Oh, really? Oh, it's still going though. It says low power, but. Oh, I have a little charger thing too. Okay, so this is a electric force. It's related. Please, please, please. Yes. Right. So, electric force. And I'll say this, that by studying all these laws, then people started thinking about the world, and then they started to study the electric force, and et cetera, et cetera. And so this does lead into, I don't know if that's going to work, but let's just hope it does. Let's give me some charge. Okay. It leads into all of our developments. This literally changed the world, because when you start studying this, it's great. This has got low mass, but it doesn't go forever, but it would. Except we're used to air resistance, so I throw something and the air will slow this down a lot. It doesn't slow this down much, the air doesn't slow it down much. So we studied that a lot, but just get the idea and try to believe if it's a contest between your intuition and Newton's laws, trust Newton's laws. Aristotle was wrong, etc. Trust, they've been tested, right? So what's this? It's turning, right? It's the wall right here that pushes on it to turn. If I take the wall out, instead of building the wall, if I take the wall out, it'll go straight. It doesn't go out, it goes straight. If you spin around and you let go, you go straight. You don't go out. So we think we go out. We think there's a force called a centrifugal force. Centrifugal just means outward. That gets said incorrectly so much on YouTube, etc. We have these great people that are engineers or they're race car drivers or they're motorcycle drivers, and I like to listen to them, but it just they get their physics wrong. But they get the engineering right in the end. But there's nothing pulling me out. It feels like there's something. No, there's nothing pulling you out. You're turning this way. You got to either be pushed or pulled in to turn. What you're feeling is not something pulling you out, and mass does not pull. What you're feeling is you want to go straight. So you start turning, right? You go in a car and you start turning. Your body wants to go straight. And you go, oh, wait, I want to go straight. And it feels like it's out compared to in. It's not out, it's straight. Your body wants to go straight. There's nothing pulling you out. Now, there can be, right? If I grabbed onto one of you, or you grabbed onto me, whatever, you'd be pulling me out. If you win, I'd have to let go and I'd go that way. You could be pulling me out, this could be pulling me in. Let's not worry about that. So it gets a little tricky, but the natural tendency is for things to go straight. Everybody cool with that? They will go straight forever. Don't worry about how it got moving. Once it's moving, so this is like hitting ice. You hit some perfect ice, you're driving. If you step on the gas pedal, your tires will spin real fast, but there's nothing to push on, so you don't go faster. Slam on the brakes, your tires stop, still go. Turn the wheels, your tires turn. But if there's no friction at all, which we don't experience much, so we're not quite used to it, mud or whatever, you just keep going. Okay, so that's what that says. So the conclusion is, and you're going to see where this leads, it's going to be crazy. In order, if anything is ever changing speed or direction, there must be at least one force, maybe a bunch of forces. They can't be in balance, and the unbalanced force will cause the acceleration. But that same amount, that same strength of force will cause less acceleration, less abrupt, on more mass. Is that okay? You can actually learn this stuff intuitively, pretty much. So you can feel that. You know pushing a kid versus an elephant. Okay, now, let's do Newton's third law kind of quickly, and you're going to experiment with this one to create this. Newton's third law, write it this way. Has anybody ever heard of Newton's third law? Action and action, reaction, equal and opposite force. Horrible phrases. Whoever teaches that should be slapped. No, I'm just it leads to mistakes. This is the way I'm writing here. You will always be right. Remember, trust Newton, not your intuition. I'm going to trick you though. Newton's third law says this. Oops, not yet. I'm right. The force. So I'm going to write force, and I'm going to say from object, which I'm going to give a name, on some other object. There's two objects, one's pushing the other, you're pushing the elephant, whatever. And then we're going to compare that to the force from object, OBJ, on OBJ, object, whatever. Let's do an experiment to see this. Because it's misleading because we're not looking at the right thing. It's really hard to discover new ideas. It's a little easier to learn them because we don't have to discover them. Because you don't know what to look at. Okay, fingers, touch your desk with your fingertips, whatever. Touch your desk or whatever, and push down, lightly. What direction is the force from you on the desk? Down, you're pushing down. Is it pushing you?
No, you're pushing.
No.
You're pushing it, but isn't it pushing your fingers?
No.
No. So pushing is not an action. And I want to get at that. It's not an action. Like, I don't expect the desk to walk, get up and slap me or something. But when I push it down, notice, I can't, look, I push the board in. Isn't it pushing my fingers back? So push harder. Push down harder. Do you feel it pushing you harder? It is pushing you harder. Feel it. You got to feel it. You cannot do it. The head is weak. Logic is weak. If that's all you got, that's fine. But experimentation, this is the profound thing. You got to feel it. Now watch this. Slap the desk lightly. Which way did you hit it? You hit the desk down. It hit you which way? Up. It's a force. That is a force. A push or a pull. You pushed it down. It pushed you up. Right? Now hit it hard. Hit it really hard. Did it hit you harder? Did your hands sting more? Yes. If you hit it harder, it will hit you back harder. It doesn't have to have a will or a consciousness to do it. Just walk into a wall and then walk into it harder. It's going to hit you back. It always hits you back. In fact, the truth of the matter is that the force from object A, your hand, on object B, the desk, compared to the force from the desk on your hand or any two objects, what can you tell me about the strength? The harder you hit it, the harder it hits you. So, is equal in strength. What about the direction? Opposite, right? You hit it down, it hits you up. And that is always true. Always true. And now, okay, and you just keep slapping the desk until you get it. It's like, oh, okay, finally I get it. Now slap the person next to you. So, right, or someone punches you in the nose. You get to say, I hit you as hard as you hit me. Right? So, the fist hits the nose hits the fist. The effect can be very different. The effect can be very different. Watch, I'll show you. Who gets hit harder? The juggling ball or my hand? Who got hit harder? Same. Who got affected more? The ball. Although I might go, ow, whatever. Depends on what you mean by effect. But why do you think that would be true? Kid runs into an elephant. Who got hit harder? Same. Who got affected more? Why? Not weight, mass. Weight's force of gravity. So, the effect is what confuses us. An object with less mass, and let's not overthink this, but I'm just going to say no other forces. So imagine no other forces floating in space. The object with less mass will get more or less acceleration. The object with less mass will get more acceleration. But the force is the same. The effect is very different. We're going to see that in astronomy here in just a second. Mike?
So equal and proportional. Did you say that?
I just say it's flat out equal. Flat out equal in opposite direction. No matter what. Whatever you hit, it hits you back the same strength. The effect will be very different. And then, we can you talk about effect in terms of pain and bloody noses and things like that. But you still hit someone just as hard as they hit you, right? Oh, I saw a weird accident yesterday. Anybody know what happened in Illustrator Richmond, Florida? It looked like a car bomb went off inside. It was, anyway, sorry.
Today?
Yesterday. Really weird. And actually, they were out there measuring that, and you can use physics to kind of figure out certain things. Anyway, here we go. This is true. All right, so now let's just discover this a little bit. Think about driving. You're driving down the freeway, straight stretch, Highway 5, going down to LA, whatever, and not turning and keeping the same speed. Which law applies? Same speed, same direction. What law applies? What? Are there forces? Stick your hand out the window, you feel the air, right? But you got to keep. What happens if you take your foot off the gas pedal? You will slow down, right? Why? Because the air is hitting you, right? So that would be here. You're slowing down. Anytime you're slowing down, speeding up, or turning, this is here. There's got to be you got to blame someone. There could be lots of forces. If you go faster, the air hits you harder. So you got to keep your foot down farther, even just to do this. And your gas mileage goes down because the air hits you harder. So with speed, right? So there's lots of things, and we study that in physics classes and so on, but you just get this idea. So now you're driving down the road, especially like in the South. I hear that there's like big bugs and stuff, flying bugs and stuff. So we got some easy here in California. So a bug hits your windshield. Okay, who got hit harder? The bug or your car or the windshield?
Our car.
That's the rule. You can break the speed limit, but you can't break Newton's laws. Who got affected more? Yeah, probably the bug. We get confused by the effect. Right? The bug got hit. What's this got to do with astronomy? A lot. Is Earth accelerating?
Yes, it's turning.
Yeah, it's turning. That's number one. I mean, it is, we know it's the orbit is slightly elliptical, pretty close to circular. It slightly changes, increases speed, decreases speed a little bit. So there's a change in speed, but it's certainly turning, right? Newton's first law, second or third? First or second? It's turning. Is it accelerating? It's got to be two. This is no acceleration, this is acceleration. These are the only two cases for Newton's first law. You might have a bunch of forces, but they're balanced. This is Newton's second. But who do you blame? You could be like Aristotle and so many others, like, oh, that's just what they do in the heavens. Things go out, but they thought it went around Earth. What force is making it turn? Like when I grabbed onto this and went around. What force is making this turn? Gravity is the force, and who are you going to blame? The sun. Why? Who else are you going to blame? How does that happen? How does the sun pull on Earth? Newton didn't know, so it's okay if you don't. Einstein said he warped space-time and da-da-da-da-da. But it's not obvious, right? But you know that when you do these experiments, things only accelerate if there's an unbalanced force. And if we're going around the sun is pulling on Earth, right? Everybody cool? You got to accept that, right? I dropped this. Is it going to accelerate? It's not moving, then it starts moving, right? It's going to go faster and faster and hurt more and more as it falls further and further. Well, that's this, not this. Falling is not a natural thing. Who makes this fall? Earth, by the force of gravity. You have to invent gravity. You can't see it. All I can feel is how strongly I have to pull up or push up. And I assume that gravity pulls the exact same strength the other way. Now these forces are equal in strength in opposite direction. They are not Newton's third law. Newton's third law says I pull on the object, the object pulls on me. I don't get too much into that, but I'm going to go here. That's a tricky one. That's why the phrase is so bad. Sun is pulling on Earth. Everybody kind of go along with that? With the force of gravity. Newton wrote the equation. We're going to talk about that real quickly. Because when things accelerate, you got to blame it on someone. Kind of what? If Sun is pulling on Earth, then what's true also? Earth is pulling on stronger. Who gets pulled stronger? Equal. Who gets affected more?
Earth.
Why? Has less mass. Sun wobbles a little bit, but it's got a lot of mass compared to Earth. We're just a little grain of sand compared to, if Sun was that size, it would be a grain of sand. And that Sun pulls on us and we go around it. We pull on it, it's like, whatever, like a bug hitting your windshield. Okay, but we are pulling equal strength. The effect, okay, is Moon accelerating? Who's making it?
Gravity.
The force is gravity. That's right. Force is gravity from, who are you going to blame? Earth, right? What else you make it up and you see if it works. That's what he did. Like, I don't know how. He didn't know how. But he wrote an equation that worked. And when you put that equation together, you get Kepler's laws for how planets move. Kepler didn't know how. He said, I don't know, they're moving like that. Newton said, let me write some math equation that gives me your result. Because I know your result's the way it is. And he wrote that equation. And then poets wrote about Newton, like, oh my gosh, he just opened up the universe for us. Earth is pulling on Moon. What does that mean? Who's pulling stronger? Equal. Who gets affected more? Moon. It's 1/4 as wide. You'll learn that later, but 1/4 as wide. Gets affected more. And it's getting pulled by Sun. In fact, if this was Sun, I'll put this at the back wall. This is at the back wall. Earth is here, a grain of sand. And you cut that grain of sand in half, and then take a half and cut it in half. That would be Moon, and it would be right here. So as we orbit Sun, Moon is right next to us, and we're going to build that intuition. It's so close that we can go up there and back in a week. Spring break, extra credit. So that's, use these as a gauge. Again, the third and fourth time it starts making sense. Doesn't mean you won't be tricked, because we haven't spent a ton of time. But you have to invent a force. You've got to blame someone. And so we invent gravity. And then you keep going, and it gets deeper and deeper, and we get cell phones. So that's the short thing. Is that, Casey, is that still working?
Yeah.
Okay, so here we have this. To conclude, you invent gravity. And so you're going to get two of the key players of the universe. These are the laws, as we know them, of the universe for matter, objects with mass. Which is funny, happens with light, too. We wouldn't expect light to be affected by gravity, but it is, and Einstein predicted it.
What if you can't find somebody to blame?
I won't go political with that one. There has to be some. Or, and this is a good question, because as people do this, what you do as a scientist is you don't accept anything. You get really annoying. And you test things. Because if you can prove Newton wrong, you're going to be famous. Einstein's famous, right? So it's not that he was totally, I mean, we use Newton anytime we can. It's much simpler than the more complex ideas. But we dig deeper. But still, that idea still holds. And there's something deep about interactions. So then we look at light and dark matter and dark energy. We're still working on it. I mean, that's kind of the fun that I like of the puzzle of that. But I like sharing it too. So yeah. So as far as we know, you still got to blame someone. But it's a super deep question. So to understand it and to ask these kind of questions is you're getting it. When you really get it, you realize, well, I still have questions. I'm not totally clear. Okay, cool. Universal gravitation. Here's what Newton. Universal gravitation. Newton's mathematical law gives Kepler 1, Kepler 2, Kepler 3. In fact, it's designed to match that. If you use Newton's laws and you write this equation for how strong gravity is, you get that, which is amazing. And then you apply it to a comet, you can say how long it's going to take to go around, all kinds of things. This is without computers, so that's pretty impressive. And what that says is that all objects, matter, I'm talking about, not light, pull all other objects, matter. Again, light is affected, but that wasn't known here, and that has to do with more Einstein. And they do it without touching. That's weird. That's like magic, but it's true. You can test it. And there are 3 factors. And it makes sense. If all objects are pulling, you with me? Then this is pulling on you. And this is pulling on you. How much is the pull if I put them together? How much is the total pull if we have one pull and another pull? Twice as much, right? Because if one can pull it. So the point is that the more mass pulling gives a stronger pull. More mass pulling gives stronger pull, and that is proportional. If you double it, you get twice as much. It kind of makes sense. One kid pushing you, 2 kids pushing you. And teaching elementary school, you should get paid twice as much. So, and this is a weird idea. Prior to that, it was like, oh, that's the heavens and they operate on different principles. Now we're saying out there, all this stuff works. And everything pulls. That means you're all pulling on me. It's exhausting me. And I'm pulling on all of you. That's even exhausting me more. And you're pulling on everybody in the room. Do you feel it? Well, we kind of get to the blame thing again. You probably can't blame that because the pull's really tiny. We can measure it. You can measure now. It's really hard to measure the pull between these two. It's really, you don't see it. It's just not in our sensory experience. It's really tiny. But it's crazy that now with our technology, et cetera, we can measure that. But everything pulls, but it's super tiny. You need a lot of mass like Earth. More mass being pulled and it does lead to questions. And Einstein wondered. He just obsessed about it. So that means if you're pulling this one, right, and you're pulling this one, if I put them together, you're pulling the object twice as much. You're pulling this and this. But it's not pulling in an action like you're going to get tired. So it's an interesting weird thing. Just let that sit. It's pretty weird. But the more mass being pulled gets pulled stronger. Now you know this. Which of these do you think would be easier to throw? The one with less mass, right? So clearly. So that's accelerating it. Which of these is harder to hold up? This one. That's a different thing. The first one was inertia, how hard it is to speed it up. The second one is balancing the pull of gravity. This one is being pulled much stronger than this one. Why? It has more mass. They're about the same size, but there's something about it. It's got more mass, clearly. If you go to moon, and we're going to hit this again in chapter 6, but I'll go ahead and preview it. So if I, near the end of the chapter, that's chapter 4. Chapter 3. Near the end of the chapter. A lot of exercises in there to help you drill this, challenge it, and there's solutions or discussions in the back of the book, so do that. Where did you go? Here it is. So, if you step on a scale on Earth, and you weigh 240 pounds, and then you go to moon, you're in a room, so you don't have to have a spacesuit or anything, and you step on the scale, moon has much less mass. In fact, it will pull on you almost exactly 1/6 as much. It's not much of 1/6 as much. So you step on the scale in a room with air and stuff, and it'll be 1/6, so 24 by 6 is 40, so 40 pounds. Wow, 40 pounds. Why? Because it's pulling you less. You have the same mass. Mass is not weight. Weight is the pull of gravity. On Earth, your weight's 240. You're at 40. Divide by 6, 180. So I step on a scale here, it's 180. I step on a scale moon, it says 30. 120, 20. I'm going to do an infomercial. Weight loss. 5 payments, $29.95. I'll tell you how to lose weight. Just go to the moon. Because you don't have weight. You're still going to have the same mass. It's this weight. So it pulls on you less. This experience of weight is being pulled, but we don't feel like someone grabbing onto us. It's a really weird, deep thing. Kind of like the chapter 0 stuff. So don't be, just go with it. Just go, let it, just be tickled by it like it's a curious thing. And that's it. Okay. There's one other thing. If you have more mass, you're going to get pulled more. This guy gets pulled down. How do I know it's pulled down? Because it's got to pull up to keep it in balance. Newton's first law. Now it's got twice as much mass. It's got to be pulled up twice as hard. Why? Because it's being pulled down twice as much. You cool with that? Interesting thing, though, when things pull on each other, and again, no matter how big or small, but the small ones don't pull much, so you can't see. As you get farther away, well, tell me this. As you get farther away from light, what do you see? It looks dimmer, right? As you get farther away from sound, it sounds softer, right? Think of the sound and it's spreading out over a larger surface. As you blow up a balloon, the rubber walls get thinner and thinner because it's spreading out over a larger surface area. Light spreads out over a larger area. In gravity, Newton's law, although it's not exactly right, gives us a way of thinking about it. Gravity also gets weaker with distance. And so, this next one is that the pull, the last piece, the grav pull, gets weaker. This is going to lead to something really cool. Gets weaker the farther apart the objects are. We call it an inverse, which means weaker, square law. We're going to see this for light again in chapter 10. Don't overthink it. You're not going to do calculations here or anything. But still, the crazy thing is, if you double 2 times the distance apart, the separation, double the separation, the pull gets 2 squared, that's the square, inverse square. 2 squared equals 4 times weaker. What if you triple the distance? What's 3 squared? 3 times 3, 9 times weaker. 10 times the distance, 10 times 10, 100 times weaker. And that law gives you Kepler's laws. But it has to be modified, especially Mercury, where the gravity is strong. So as it gets farther away, it's pulling weaker. So, you know, this is pulling on my head, and now it's pulling weaker. You can't feel it. It's crazy. And you test it, and you find out, yeah, it works. All right, this leads to the very last part of chapter 3, and that is, any questions? There's a level of you just got to accept it. Now, it's good to challenge it as a scientist you can, but you don't have time to, so you got to accept it. You go do experiments and everything, and usually what we do is we figure out what everybody else has done, so we don't repeat necessarily. We got to come up with some clever experiment that we can do. Okay. This leads to a tiny extra effect from gravity, which is a key player in the universe. Lots of things happen from this little thing. It's not hard. You get this. Let me write this. We can call it the tidal force, or you can call it the tidal effect. It's kind of 2 sides of the same coin. And I might ask, what's the tidal effect in general? Here's all it is. With me? Why does Earth turn? What's our story, Lee? Sun's pulling on it, right? But wait a minute. Now, Sun and Earth is a grain of sand, so there's not too much effect here. We'll talk about this at the end of chapter 4. We're going to come back to this at the end of chapter 4 and use it to some cool things. What side of Earth would Sun pull stronger on? The near side, the close side, we call it the near side, or the far side? Which side would it pull stronger on? Because why? Gravity is weaker with distance, right? Earth is pulling on Moon, right? Which side of Moon does Earth pull stronger on? The near or the far side? Because it's closer, that's all, right? And weaker on the far side, right? Wait, if Earth pulls on Moon, then Moon pulls on Earth, right? But here's the key. Moon pulls stronger on which side of Earth? The near side, right? That gives us our ocean tides. So the answer here is that the grav pull on the closer, near, I'll say parentheses, we call it the near side, compared to the grav pull on the farther, so we call it the far side, is what? The pull on the near side is stronger than the pull on the far side. That's all. Why? Because, why? Tell me. Gravity gets weaker with distance. Now you understand the title effect. What you're going to see, and if you read the end of chapter 3, I just threw out a whole bunch of effects in the universe because of this. Crazy things. Huge play. Might even create places where there could be life because of this. Surprised us around 1980. Where there could be places for life because of this extra little bit. And that's going to be cool, but we're going to hold off on it. All right. You okay? Now you know some of the laws that this is the, to me, this is, at this point, it's a scientific revolution. Game on. We start thousands of years. We get to this place, in just 300 years, we've got cell phones. So, and we're learning faster and faster and faster now. So it's crazy. Review that. It's a lot of information, but if you review it, it'll stay. Now we've got a big challenge. Write this down. It's going to be quick. I'm going to see if this video comes out. If it doesn't, we'll just be quick. You have this in the book some here. Here's the challenge. Here's what we're going to do. We're going to piece it together. This is the challenge. Of chapter 4. Maybe the most challenging. Chapter 10 is a little challenging too. And I'm going to try to, I'm going to try to lay this out because it's hard stuff. You teach it like it's obvious. It's not. Chapter 4 challenge. The Earth, Moon, and Sun dance. Why we see what we see. Why we see what we see. So a little quick review. If anybody didn't pick up their exam, I do have things. In chapter 1, so it's nice, we get to review, and then we're going to change the game after chapter 4. We're going to study worlds, compare Earth to Moon, to Mars, to Mercury, think about other worlds, and study stars. So chapter 1 is all about what is seen from Earth. And we use what I call your sky, which is just standing out there. You got ground, you got horizon, you got sky, you're looking up, you're wondering, you got sheep. What are you going to do? And that's, we're going to try to connect, not entirely, because it's quite a challenge. It takes you a little time, more than 4 months, especially when you're doing other things. But we are still going to connect this with chapter 4. And what's chapter 4 about? It's seen from a spaceship. It's what's actually going on. What's actually going on. So when we go outside, let's do a little quick review. We go outside, you know, you go like this, and here's your ground, there's you, and there's your sheep, whatever, like that. And in whatever direction, you can put south anywhere, I'm gonna put south. And this is north. You're facing south, you got east on the left, west on the right. If you turn around, now west is on the left. And you look up, and of course you got sky up here. That's too hard to draw, so we draw like this, and we go eat sandwich. There's our ground, we're facing south, that's facing south. You've got your sky up here, and everything, sun, moon, planets, stars, in one day, at night, everything's gonna rise somewhere around here. Sun, it would be June, July, August, September, October, November, December, January, February, March is the same as September. April, May, June, it goes back and forth. You only need 3 for the solstice, equinox, solstice, equinox, solstice. Review that, but anything, planets, everything comes up and over like that, and that's what you see. However, if you turn around, it's something interesting, and you're wondering why, because it's not obvious. Now, on my left is west, and what is that star in the northern horizon that I can follow to guide me? Polaris, magnitude 2, that's the stuff you gotta hold on to. The only way you hold on to it is repetition for the exam. It's a lot of information, but you can do it. It's pretty amazing. So, and believe me, there's so many times where they have thought, I can't do this, there's no way I can do this. But you do keep doing repetition, and it's like, I can't believe I know this stuff now. But it's endless. And things rise up then. Now, instead of rising east over here, they rise here, but they don't go like this. They go around, up and around, and just around, right? And so that's what you see. And you're wondering why. I don't know, I just see this. I got a calendar from this, and we're going to talk about that. So in chapter 4, we're going to answer these questions. I would put it here, but let me put it over here so that I keep my list. Let me get rid of this quick. Chapter 4, we're going to do this in different order. 4.2, why the zodiac? That is, why do we see sun, moon, and planets only in one strip of the sky? That was one of our puzzles. 2, 4.1, 2 meanings for year, day, month. No, I'm going to do it this way. Let me write month, cross it out, and moon cycle. Moon cycle. 4.3, I have it on YouTube. We're supposed to cover that next week. Why seasons? Some drawings. 4.4, why and when moon phases? Why and when moon phases? That one's maybe one of the hardest ones to get because I go pretty far. Drawings will reveal it. 4.5, why eclipses? That's super fast and easy. And 4.6, tidal effect. So just write this as an outline because that's the start of understanding. And that's going to be from Earth on moon, and then from moon on Earth. And right when your head's about to explode, we'll have exam 2. But trust, when it starts making sense, it's the coolest feeling ever. So we're going to connect what we saw with this. We're going to answer these questions finally. Why is this going on? Make sure you review, because like right now you've had too much information. Newton's laws are getting a little jumbled in your head. You know, I get it. But as you review, it's easy. We have students that never took physics in high school. They think they want to do engineering. They take our physics class and we just beat them up. They fail. But they know they can do it. So they retake it, they do it, they move on, they do incredibly well. And at university and they excel. Tick. They represent country custom. Big time. So it's like Wizard of Oz. How many people have seen the movie Wizard of Oz? Just curious. It's so worth it. And then watch it with Pink Floyd. Anyway, I've never actually done that.
It doesn't work.
It doesn't work.
It only works with
Number 4.2. Why the zodiac? I'm going to make this fast. You can read the book too. Look. You gotta have it up high. It's going to be done. Here we go. Look. Number 1. It's heliocentric. It's, no one. We're done that argument. The Earth is not flat. If Earth is going around Sun on the same level, not some wacky way, and all the planets are going on that same level, then as you go around 1 AU away, light years away, the stars behind Sun will always be the Chapter 4 stars. And then you come around here and it'll be the smudge stars. And then the whatever stars. And as you go around, it'll be in front of those stars. And as you go around, Sun will always appear in front of this strip, right? Because you're going around it. You're never going to see Sun in front of those stars because they have to be here and you'd be like, what? Or those. You only see Sun in front of that strip. And also, if you have other planets that are going around in opposition and conjunction and wherever, those planets are on the same level and they're always going to be in front of that strip too. Done. That's why we see them in the zodiac. There's nothing, you can cut it up any way you want. You don't have to use the Greek zodiac. I mean, there's lots of other cultures that we can learn about and appreciate. So here's a kind of picture in the book. As we go around, everything is on the same level. And so they're all going to be in front of that strip of stars. Cut it up how you want. Chinese didn't use 12. They were okay. Still working. Hey. All right. Everybody cool with that? That's it. One thing that's interesting is when I'm here and there's Sun, am I going to see those stars? Am I going to see those? Right? So during this season, whatever it is, I get to see those stars. I get to see the Kevin and Casey stars. Right? That constellation. Right? 6 months later, 3 months later, right? And every day I'm doing this. Oh, look, nighttime, right? I got the sunlight here. Daytime. Oh, sun's rising. Look, sun's going around me. No, it's not. And then every day I'm going to move about 1 degree, tiny bit. Nighttime. Oh, I see these. Daytime. Nighttime. Daytime. Sunset. Sunset. Night. You can see those. Sunrise. Noon. Noon, right? You don't believe me, you'll believe her. Noon. Okay, cool. And she's spinning eastward. Oh, things are rising in the east and setting in the west. Oh, I get to see those stars. I can't see those stars now. I can see these stars. 6 months later. Now I can't. Oh, wait. 6 months from there. Now I can't see Casey and Kevin. I don't see them, but I get to see, now I get to see the board. I couldn't see the board over there, right? This answers everything. Everything that we see is answered by this heliocentric. It makes sense. The only thing that doesn't make sense is it doesn't feel like we're moving. And the reason is we're making a very big round turn. It's very gradual. Even though San Francisco travels from spinning 700 miles an hour, the equator is 1,000 miles an hour, and 100 times faster than 700 for orbiting. It's a very smooth ride. Our air comes with us, but it does circulate under it, creating weather patterns. So very measurable. This is high on the certainty scale. Everybody okay with that? This year is a what? Leap year. Cool. So let's create this chart. Ready? Do it. least 20 years. Year, day, moon cycle. Approximately a month. And we're going to have seen from Earth, 2 columns. Seen from Earth, Chapter 1, and what we use daily. And then 2, seen from Spaceship, Chapter 4. Seen from Space Ship, Chapter 4. I'm going to write 2 things, 2 sentences. What is actually happening? What is actually happening? In particular, we're going to discuss the time, different times, but the time to go around once. Okay. What do we use to talk about a calendar? What do we use to talk about a year and know when to celebrate New Year's? A what? Calendar, right? You use a calendar or phones now. Okay, a calendar. So, a calendar. Okay, great. We use a calendar. And by the way, calendars were created by watching those paths of sun, right? They never cross, by the way, never cross, right? Meridian right there, before the meridian, sun is before the meridian, sun is that past the meridian, AM, PM. That's how we create our calendar. How many days in a calendar year?
365.
365 days. That means well, we'll see about that, days. Except what? Leap year, like this year, where you do what? Every 4 years, add 1 day to who? Because February got ripped off. We'll talk about that. You can make up calendars however you want. Doesn't matter how you make your calendar, that's going to happen. The sun's going to rise and set. It doesn't care what you call it. We make our months connected to moon phases, but not exactly because it's not a perfect fit. All right. What's physically happening to give us a year? I just demonstrated it. What's physically happening in 1 year? Earth goes around sun once, right? So, okay, Earth orbits sun once. Anybody see that movie once? I love that movie. Oh yeah, they redid it, didn't they? Did they redo it? Yeah, they did. With what's her face? With come on, someone knows. So good, so good. You get back to the same place. In how long? 365 and a quarter days. That's about 365, that is 365.25 if you want. This is parenthetical, you don't need it. Actually, it's not even that correct, 365.24 days. Anyway, here's the point. check it out. You can get this. 365 days to go 360 degrees. We move about 1 degree, a little bit, right, a little pinky tip, every day. Little by little, creeping around. Now, whether it's your birthday or New Year's, let's use New Year's, you'd like to be in the same place. So here we have Happy New Year's. Boom. All right, there it is. Now, Monday on January, February, March, the season, third of the way, 3 months, 4, 5, 6 months, 7, 8, 9 months, 10, 11, 12. Happy New Year! Wait a minute. That doesn't make sense. We're not back at the same place. We're short by a quarter of a day. How many hours is that? 6 hours. So we're not really back to the same place until another 6 hours. But wait a minute, so we still celebrated Happy New Year's. We're not going to wait for that. And then we go down, 1 month, 3 months, 6 months, 9 months, and Happy New Year. Uh-oh, how much are we behind now? 2 quarters of a day, right? 12 hours. And you go, Happy New Year, and we're back. Oh no, 3 quarters of a day short. That's really exaggeration because every day is only a degree. 3 quarters of a day, and you go around again, and you're 4 quarters of a day or 1 day short after 1, 2, 3, 4 years. If you let that drift, it'll take a while, but all of a sudden, January would be summer. We know we're closest in January, but not that much closer, so it doesn't make us have summer. So what do? We add a year. That's all. Okay? There's the time to go around, which is not exactly 365 days. So we got to adjust it. And we actually have to adjust it even more than that a little bit. Do you have to know that? No, your phone takes care of it. Okay, now, one other thing. Ah, we're so close. And I'll have to do this on YouTube. But let's explore this. So this is the part that's a challenge. We're going to have to piece together a lot of things. Each piece can make sense. Each piece can make sense. The side of anything facing the light bulb is lit. Half of it's lit. Anything in space, all the planets, etc., are half lit. Right? Everything is half lit. The other side is dark, and there's a terminator separating the lit and the dark. Everybody buy that? This side of me is lit. You guys see whatever side is the near side to you. Whatever side is near to you. If I'm spinning, I'm still always half lit. It's just different sides. We're not going to worry about spin until the end of this chapter. So whatever's in the light is always half lit. Terminator, dark side, cast the shadow. Everybody cool with that? Just like do that. Get a lamp, use the exercises. Now, if I do this real fast, just to get you going, because I'm not going to see you for, I don't know when. It's very, very weird, but we're doing it for the greater good. Where is the light coming from? Where's the light? This is a ball. This is the dark side. This is the terminator lit side. Where's the light coming from? Down below, so I'm going to draw arrows. Here, where's the light coming from? Here, where is it? Here's where you got to be careful. Some of you are like amazing artists and things like that. But it can't be up, it can't be that way. It's got to come from here. It's got to come from here. It's got to come down like that. Everybody okay with that? So one last little quickie. I know, you got to go, you got kids, whatever. Can you draw the terminator and shade the dark side? Where is it? Is it here? Is it there?
No.
Tell me when. Okay, what about here? Right, boom. So you can do that. So that's an awareness you just have to have. Now, you know that everything around the sun is half lit, but it's the side facing you that you see. And you know that this ball is half lit, and yet the side facing you gives you phases. From space, you see a moon that's always half lit. You don't get to see phases. You need a text message from your friend to show you the phases that are seen from Earth. So we'll work on that. I'll send you lots of emails. Make sure you check your emails. And we'll roll the best we can. So stick to that schedule.